working on this, understanding this band structure, and I'd like to finish up today on talking about these service electronic structure, and maybe next day we'll talk a little bit about the mission and move on from there. Okay. We have maybe 3 to 4 more lectures to go. I think we'll try to finish up a little bit early if, to give you guys some time to work on the term paper. People did not do very well in the first assignment. I'll give you back the assignment next Tuesday. So a solution for assignment 1 was posted, and I'll post the solution for assignment 2 very shortly on this. And you have the new assignment, the last assignment was posted on the web, so you can take a look at that. And I think after today's lecture, you probably can do this assignment. Should not be a problem. Then involve a little bit of looking at things on your own for the last assignment, because you involve a little bit of start math about the helium-3 problem. But you can, pretty sure you can find these in the standard textbook on this. Okay, so last day we were talking about these free electron gas models. So I've been perhaps belabor a little bit too much on the origin of this so-called band gap. So we started talking about in the free electron model, you have this parabola, this is the parabola that you got, and when you plot it this way, when you plot it in K space, right? So this is K space, and you plot the energy in this direction. So that's what the commonly called a band structure. When you plot everything over from -infinity to infinity in the K space, that is known as extended zone scheme in showing the band structure. And of course, that is a little bit impractical because it's hard to show everything to infinity. So people come up with the idea that, well, maybe you can fold this together into the first Brillouin zone. So if you fold these together, this extended, parabola get folded. This point get folded to here, and this one get folded exactly like you folding newspaper, folding paper. You fold it to here, and then all you need to do is just consider the first Brillouin zone. And so that's called a reduced zone scheme, and all the information is contained, in fact, is contained in the first Brillouin zone. Okay? So that oftentimes when you read the literature, this is what you see. When you look at the band structure, this is what you see. People just show the first Brillouin zone. Why you can do that is because if you think about it, the structure is periodic. So if you reproduce, let's say this is, I'm just looking at one center here. If you duplicate by the same periodicity, you shift it to here, and you duplicate the same thing, you see. If you move this point by the same amount, you duplicate your band structure like this. You can see that this is exactly like as if you fold it on here, right? So you cannot think in terms of one point in isolation, because you have multiple points along the periodicity. And so if you consider all the multiple points, in fact, you would have these reduced zone schemes that you see, because you will see, because the reason is that the other center is contributing to this bit here. You can sort of think of it that way. Okay, so that's a interesting thing. I think it's a useful thing to realize for the purpose of this course. When you're looking at electronic band structure for a solid, you will see this. And for the one thing that I like people to recognize is that for a solid, your electronic band structure for a free electron is parabola. The reason why is we showed this last day when we try to solve the particle in a box, and then we start out with free electron first. The reason is that, you know, E, you're talking about kinetic energy here. E is proportional k squared, and k squared, of course, you're plotting k in the x direction. You know, so it's a parabola. You know, that's the simple reason for free electron. So once you see a free electron, you know right away you're dealing with a parabola, and this is always true. Okay. So now from that point on, it's just a modification then of this parabola, because now you no longer have free electron, you have potential in your solid. So what's happening is that you have modification to this free electron scheme. So you would have things like this. You would have creation of the gap, right? We talk about one-dimensional box and then two-dimensional box, and the effect of two-dimensional box is that it split the energy level and you create this box, this gap, and this gap lead to a characteristic of periodicity. And why you have this is fundamentally is because of boundary condition. Because one region of space has to, the wave function has to change smoothly from one region of space to another region of space, right? Fundamentally, that's what quantum mechanics says. We cannot have abrupt change. We cannot have discontinuity of my wave function going from one space to another. And that's those kind of boundary conditions fundamentally created these gap splitting of energy level and so forth. Okay, so that I think even if we don't understand the math, we should try to follow through qualitatively what the origin of the band gap and these band structure in that way. And we also sort of look at it from the LCAO MO point of view. I go very quickly last time to talk a little bit about this structure. We think about, you know, when we're talking about linear combination of atomic orbital to molecular orbital, we think we learn these things perhaps in not such a mathematical detail in first year chemistry courses, and there we say that, okay, we have a linear combination. So this is, think about my molecular orbital, this is my atomic orbital, and then I have some coefficient, you know, this is my coefficient in front of this orbital, and I just sum them up, and I adjust my coefficient in a way that will suit my need, right? So that's the basic LCAO-MO approach. Very powerful concept in chemistry. It's being used daily, I'm sure, in chemistry community to think about chemical bonding and things like that. And in that formalism, what people come up with is that your energy will simply work out something called the expectation value. This is a well-defined scheme of working out energy from your wave function, and it's written as two integral, essentially the division of two integral. You have a density. This corresponds to, if you like, the amount of electron. So equivalent to the probability of the amount of electron in this molecular orbitals, right? And this is the probability of having a certain energy. That's what this integral is all about. And then if you expand these two integral into using this linear combination LCAO, linear combination as atomic orbitals. Remember, this is my atomic orbital. You would get some small summation sign, right? So you have coefficient in front, and then you have some value, and this value is an integral of your atomic orbital, involving integration, right, of your atomic orbitals. So we take an example here using, we try to make sure that we don't, in quantum mechanics, you try to be efficient, and the way you try to be efficient is that you try to create orthogonal basis function or orthogonal atomic orthogonal means that just like your Cartesian coordinate x, y, z, right? You don't want any